Hello there. In this video, I want to explore the ideas of minimums and maximums within a cubic equation. Now, well, a little bit to understand about me, I'm a high school math teacher, so I teach a lot of quadratics, that general form there being ax squared plus bx plus c equals 0. And in this form, we can calculate the vertex of a quadratic by taking the b value as its opposite and dividing by 2a. And then once we get that, we get the y value by plugging that back in for x if we were to define this as f of x, okay? And that's how we get it. So I was curious, is there a similar formula we could use to calculate the minimums and maximums of a cubic formula? Well, to understand how we can get that, let's try to understand how we get this negative b over 2a formula. If you have a background in calculus, then you know probably the most efficient way is to take the derivative of f of x. That would be 2a to the x by bringing this down and subtracting 1. The derivative of the bx would just be b, and the derivative of c is 0. Okay? And when you're testing for a minimum and a maximum, we take this equation, its derivative, and we solve for x when we set it equal to 0. So we subtract b, and we get negative b equals 2ax, and then we divide by 2a. And so there you go. Let me write it up here. We get x equals negative b over 2a. I'm sure there's dozens of ways to get that, but if you have a background in calculus and you know a little bit about derivatives, this would be the best way to find that out. So what would it look like for a cubic? So if we had the general formula for a cubic, that'd be ax cubed plus bx squared plus cx plus d. Now, if you haven't thought about this much, you might be thinking, well, are we going to need the cubic formula on this? And the answer is no, because remember, when we dealt with a quadratic, we take the derivative, we get a linear polynomial back. So when we take the derivative of a cubic, we're going to get a quadratic back. We can use the quadratic formula. So I'm going to go ahead and calculate the derivative. Bring this out in front and subtract 1. So that's 3 times ax squared. Do the same thing here. Plus 2bx. The derivative here is just c. And the derivative of any constant is 0. Okay? So we can use our quadratic formula, noticing that we're going to use 3a, 2b, and c instead. So we've got the negative 2b plus or minus the square root of 2b, that entire thing squared, minus 4 times the 3a times the c, divided by 2 times 3a. Okay, so let's simplify. Nothing to simplify here. That's just a negative 2b. Now here, I'm going to actually do something. I'm going to simplify here, so plus or minus the square root of 4b squared, but I'm not going to simplify this, and you may see why. So minus 4 times 3a times c, and I'm not going to simplify the denominator. And once again, you'll see why. You may already see why. Notice we have a 4 in common. Not only can I factor that 4 out, I can then also take the square root of 4, and we get negative 2b plus or minus 2 root b squared minus 3ac, all divided by 2 times 3a. Now, you could have still simplified 2 times 3a if you wanted to. It's not a big deal, but it's easier to see cancel that, cancel that, cancel that, and we're left with a final form of negative b plus or minus the square root of b squared minus 3ac all over 3a. Now, I personally find this result fascinating, and that's because while the process is not difficult, if you have an understanding of how derivatives work and where minimums and maximums exist, then what we can do here is ultimately just find the answer any way we want. We could have used completing the square. If it was factorable, we could have done that. What I find fascinating, though, is it's basically just a same replica as the quadratic formula, except we took out the 4 and the 2 and we replaced it with 3s. It's kind of like that 3 is saying, well, this is a cubic, it's degree 3. So use 3 instead. I'm not saying that's the actual reason, but I find that just little tiny minor change fascinating. And so that would be how you calculate the minimums and maximums, or at least the x locations of a cubic formula or a cubic polynomial. Now, you could extend this. If you had a quartic, the derivative of that would be a cubic, but then you're starting to get into, okay, all the ways we can solve cubic equations. If you had a quintic, your derivative would be a quartic, then you're starting to get into really hairy territory. Then you get to a hexic, a 6-degree polynomial. Your derivative is a quintic, and the quintic systems are not solvable, so you'd have to really be scrapping. At that point, you're probably just going to use some kind of graphing technology or Newton's method to find your answers. But thought I'd share that thought with you. Thanks for watching.